Hello, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for sleepy minds. Today, I will be talking about the entire life journey of a star and what happens when it comes to the end of its time. So sit back, relax, and let your thoughts carry you to sleep. But before you do that, take a moment to like the video and subscribe to the channel. And thank you so much for being here. Also, comment down below where you are tuning in from. It is always fascinating to know where you guys are watching from. So what is a star? A star is a giant ball of hot gas held together by its own gravity, shining because tiny atoms in its core are pushed so close together that they fuse into new atoms and release energy. That sentence hides a lot, so let's unpack it slowly and clearly. Imagine a huge sphere, mostly made of hydrogen, the simplest element in the universe. One proton and one electron. Gravity is the pull everything with mass has on everything else, and when you have a lot of mass in one place, the pull gets strong. In a star, gravity squeezes the gas toward the center. Squeezing a gas heats it up, like air getting hot in a bicycle pump. Deep inside, the pressure and temperature become extreme, millions of degrees, and pressures so high we can't copy them on Earth, except for an instant in special experiments. At those conditions, hydrogen nuclei, the protons, slam together and stick, step by step, to become helium. Each fusion step releases energy. That energy moves outward through the star and eventually reaches the surface as light and heat. This is why the sun shines, and why you can feel warmth on your skin on a clear day, even though space is freezing cold. The power source does not come from burning like wood or coal. It is nuclear fusion, which is millions of times more efficient. A star is also a balancing act. Gravity tries to make it shrink. The heat made by fusion pushes outward and tries to make it expand. When those two effects are equal, the star holds a steady size. If fusion slows down, gravity wins for a while, and the star shrinks and heats until fusion speeds up again. If fusion goes too fast, the star puffs up and cools a bit, which slows the reactions back down. This built-in thermostat keeps stars stable for long stretches of time. Finally, not all stars are the same. Some are tiny and cool, some are huge and hot. Mass is the key. A star's mass decides its brightness, its color, how long it will live, and how it will die. Think of mass as the star's life script. More mass means a brighter show, but a shorter run. Less mass means a dimmer lamp that can glow for a very long time. With that picture, we can start the story at the very beginning, before a star even exists. Stars are born inside enormous cold clouds of gas and dust that drift between the stars. Cold here means only a few tens of degrees above absolute zero. These are called molecular clouds because the hydrogen is paired up into H2 molecules, and the dust grains are tiny bits of carbon and rock, like smoke. To your eyes, a star-forming cloud would look like a dark patch blocking background starlight, or, if nearby, a faint bluish or reddish glow. Inside these clouds, pockets begin to collect more material than their surroundings. Gravity is always at work, but it needs help to beat the cloud's internal motions, its gentle drift, its thin magnetic fields, and its small amounts of heat. A little nudge can start collapse. The shockwave from a nearby supernova, the squeeze from two clouds bumping, or even ripples created by young hot stars blowing bubbles. Once a denser pocket forms, it pulls in more gas, which makes it denser still. This runaway growth is how a clump becomes a starseed. As the pocket folds inward, it spins faster, like a skater pulling in their arms. The spin flattens some of the falling gas into a disk around the growing center. In that disk, grains stick, pebbles collide and merge, and the first building blocks of planets start to appear. Meanwhile, the very center, the embryonic star, keeps gathering mass. The material does not fall straight in, it spirals through the disk and rains onto the core in bursts, each burst adding heat. Young, forming stars are messy eaters. They gulp material, then spit some back out as fast, narrow jets shooting from their poles, powered by magnetic fields winding up in the disk. Those jets carve holes in the surrounding cloud like lighthouses cutting through fog. From far away, the region may look tranquil, but inside it is busy. Streams of gas, shocks, jets, and new chemistry fired up by gentle starlight. This period can last a few 100,000 years. By the end, most of the mass that will make the star has gathered at the center. The disk is thinner but still present, and the core temperature has climbed dramatically. The object is not shining steadily yet like the sun. It is glowing from the heat of collapse. That glowing baby star has a name, a protostar, the main character of the next act. A protostar looks like a swollen, warm version of a real star. It is large compared to its future size and covered by a thick, dusty cocoon that hides it from regular visible light. We detect protostars mainly in infrared light, which can slip through dust better. Inside, gravity continues to squeeze the core. Every bit of gas that falls inward converts gravitational energy into heat, like water heating when it rushes down a waterfall and splashes. The protostar's surface, really the top of its gas layers, is cooler than the sun's, so it glows red or deep orange, not bright white. It also changes quickly on astronomical timescales. As material from the surrounding disk rains down, the protostar's mass grows, and so does its central pressure. With more pressure comes more heat. The goal, the threshold that will make it a true star, is to reach core temperatures of around 10 million degrees Celsius. At that point, hydrogen nuclei can fuse efficiently. While the core heats, the protostar is shedding energy too. It radiates heat from its surface, and it launches the jets mentioned earlier. Those jets, tied to magnetic fields, help slow the spin by flinging away angular momentum. Without that, the star would spin so rapidly it would tear itself apart. The disk and jets act like a safety valve that lets the core get denser and hotter. In the surrounding space, the jets plow into the cloud and light up small glowing knots where they hit, forming what astronomers call Herbig-Haro objects, signposts saying a star is forming here. During this stage, the forming star can have temper tantrums. Accretion sometimes piles up and then dumps onto the star in a sudden burst, making it brighten for months or years. Between bursts, it settles down. Step by careful step, the infall slows. The central temperature climbs. The star shrinks as it radiates away leftover formation heat. Imagine a puffy ball tightening into a denser ball. This tightening takes the protostar down a path on a diagram astronomers use to track brightness and temperature. When conditions are right in the core, a quiet but decisive change happens. The first steady hydrogen fusion reactions start. There is no thunderclap, no explosion, just a thermostat turning on deep inside. Outward pressure from fusion begins to match gravity's squeeze. That moment is the birth certificate of a true star. Hydrogen fusion is the simple idea that makes a star shine for millions to trillions of years, depending on its mass. In the Sun and similar stars, the main process is called the proton-proton chain. It goes like this. Two protons collide and very rarely stick, turning into a form of hydrogen called deuterium. One proton, one neutron, and releasing a tiny particle and energy. That deuterium quickly grabs another proton to become helium-3. Two helium-3 nuclei then meet and merge into helium-4, 2 protons, 2 neutrons, tossing out 2 extra protons to keep the bookkeeping balanced. Each step releases energy because the final helium-4 nucleus has slightly less mass than the pieces that made it. That missing mass has become energy, as Einstein's famous E=mc² says it must. There are other routes for heavier, hotter stars, but the key idea is the same. Fusing light elements into heavier ones releases energy. Now, why is this a thermostat? If the core gets a bit too cool, fusion slows, pressure drops, and gravity squeezes the core tighter. The squeeze heats the gas, and fusion speeds back up. If the core gets a bit too hot, fusion races, pressure rises, and the core expands slightly. Expansion cools it, and fusion slows back down. This feedback keeps the star stable for a long time. The energy made in the core does not leap out instantly. It bumps into particles over and over, zigzagging outward. In many stars, the inner region is radiative, where energy moves mostly as light scattering through dense gas, and the outer region is convective, where big cells of hot gas rise and cooler gas sinks, like water boiling in a pot. In other stars, especially cool, small ones, most of the interior churns. Whatever the exact mix, the energy finally reaches the surface and flows into space as the star's light. That outward flow is steady because the core reactions are steady. Seen from a planet, that steadiness is life's gift. Regular days and seasons, no sudden blaze where the star doubles overnight. The new star is now on what astronomers call the main sequence, a long middle-age phase where it quietly fuses hydrogen into helium. How long this phase lasts and how bright it is depends mainly on mass. Let's make that mass lifetime rule very clear in the next act. Mass is destiny for a star. Add more mass and you get a stronger gravitational squeeze. Stronger squeeze means a hotter, denser core. A hotter core burns fuel faster. So massive stars are like gas-guzzling race cars. They shine very brightly but run through their hydrogen quickly. Small stars are like compact cars, dimmer, slower to use fuel, and unbelievably long-lived. A star a few times the Sun's mass can live only tens of millions of years, shorter than the time it took dinosaurs to rise and fall on Earth. A star like the Sun lasts around 10 billion years on the main sequence. A small red dwarf with 1/10 the Sun's mass can last hundreds of billions to trillions of years, longer than the universe has existed so far. This range is huge and it sets up very different life stories. Color also ties to mass and temperature. Hotter stars look blue-white. Cooler stars look orange or red. You can think of a stove. The hottest part is bluish. A cooler ember is orange. Our Sun is in the yellow-white range because its surface is about 5,800 degrees Celsius. Massive blue stars have surface temperatures 2 to 3 times higher. Tiny red dwarfs are cooler by half. Brightness scales up sharply with mass. A star twice the Sun's mass is far more than twice as bright, more like 10 times, because fusion is so sensitive to temperature. This is why massive stars are rare but easy to see, and small stars are common but faint. Mass even affects how a star's outer layers move energy. Very massive stars tend to have radiation-dominated outer layers and fierce stellar winds. Cooler, smaller stars have deep convection zones and strong magnetic activity that can create star spots and flares. For planets, this matters. A planet around a small red star may face frequent flares early on. A planet around a hot blue star may not have time to develop life before its sun changes. For our purposes, we will carry 2 tracks in mind from here on: a sun-like star and a much more massive star. They share the same start but diverge later in dramatic ways. First, though, let's enjoy the long calm, the main sequence, when the star simply shines and shapes everything around it for eons. The main sequence is the star's long, steady middle age, when hydrogen fusion in the core pays every bill. For a sun-like star, this era lasts billions of years. Day to day, nothing dramatic happens. Year to year, there are gentle cycles tied to magnetism, sunspots, flares, and changing solar wind, but the total brightness barely wobbles. Deep inside, however, slow change is gathering. Fusion turns hydrogen into helium ash. Helium does not fuse yet at these temperatures, so it accumulates in the core. That makes the core slightly heavier and smaller, which gently raises temperature and pressure. The star responds by shining a little brighter and growing a little larger over very long times. On Earth, that slow brightening will eventually matter for climate far in the future, but for billions of years it is modest. Meanwhile, the star's wind, a stream of charged particles, blows a bubble in space and gradually saps the rotation of the star by dragging on magnetic fields. Young stars spin quickly and flare more. Older stars spin more slowly and calm down. Around many stars, planets form from the leftover disk early on and then settle into orbits. Asteroids and comets remain as a kind of construction debris, sometimes getting nudged inward to make meteor showers or to deliver water and organics to rocky worlds. The star's light powers weather, chemistry, and if conditions are right, life. It also sculpts atmospheres. Ultraviolet light can strip gases from small, close-in planets. Still, for most of main sequence time, the headline is stability. Fusion matches gravity. The thermostat works. The star keeps house. Only when the hydrogen in the core runs low does the story speed up. The core, now mostly helium, cannot support the star the old way. Gravity starts to win again in the center. The core contracts and heats. The outer layers respond. In a sun-like star, this begins the slow climb toward the red giant phase. In a massive star, the sequence to come moves faster and burns hotter. In both cases, the star you thought you knew will swell, change color, change brightness, and transform the neighborhood. That turning point, when the core hydrogen is gone, is where our calm chapter ends and the real drama begins in the next acts. For most of its life, a star is steady because its core keeps turning hydrogen into helium, and the heat from that fusion holds up the weight of all the layers above it. But nothing lasts forever. Very slowly, over billions of years, the supply of hydrogen at the very center is used up. The core fills with helium ash, which does not fuse yet at sun-like temperatures. Imagine the engine room switching from full power to idle, while the ship still has a long journey ahead. Gravity now has the advantage in the core because fusion there can't keep pushing back. The result is a quiet, important change. The core contracts. When a gas is squeezed, it gets hotter, so the contracting core heats up. At the same time, just outside the core, in a tight shell where there is still hydrogen, the extra heat from the contracting center makes fusion start in a shell around the core. Shell burning is like moving the campfire from the middle of the circle to a ring near the edge. This shell can fuse hydrogen faster than before, pouring more energy into the star's outer layers than they were getting during the calm middle years. What do the outer layers do with that extra energy? They expand. As they expand, they cool, the way your breath feels cooler when you blow through pursed lips and spread it out. To a distant observer, the star becomes bigger and redder, on the way toward a red giant. But the first stage of that journey is called the subgiant phase. The star is larger than before, its surface is cooler and more orange, but it's not yet the huge balloon it will become. Inside, the core keeps contracting and heating, trying to reach the temperature where helium can begin to fuse. That is a much higher bar, about 100 million degrees, far hotter than the 10 million needed to fuse hydrogen efficiently. The time from the end of core hydrogen burning to the start of core helium burning is much shorter than the long main sequence calm, but it is still slow enough that nothing looks explosive from the outside. We're talking tens to hundreds of millions of years for a sun-like star. Planets would notice the star gradually brightening and swelling. A world at Earth's distance would feel warmer decades by decade on human timescales. No, this change is still far too slow to feel in a human lifetime. But over geologic ages, it matters. The habitable zone, the region where liquid water can exist, slides outward. Ice lines in the outer system shift. Asteroids and comets feel a slightly stronger push of light. The star's wind changes the balance of charged particles around it. Even the star's spin slows more because larger stars have stronger magnetic braking. Nothing about this stage is flashy, but it is decisive. The star is now living on a ring-shaped furnace around a shrinking helium heart, climbing a gentle ramp whose end is the bright, swollen red giant that stories love to show. The star keeps feeding that hydrogen-burning shell while the helium core gets tighter and hotter. The extra energy from the shell rushes outward and puffs up the outer layers until the star becomes truly enormous, tens to even hundreds of times its former diameter for stars somewhat bigger than the Sun. For a Sun-like star, picture the star swelling so large that Mercury is swallowed whole and Venus orbits inside the lower atmosphere. Earth may stand right at the edge and is very likely lost, either dragged inward by tides and friction or baked and stripped until nothing remains. The surface becomes cooler because it is spread out over a much larger area, so the color shifts toward orange-red, even though the total power is much greater. If you could park far away and look, you'd see a gigantic, soft-glowing ball, with slow rolling convective cells the size of continents, lifting and sinking like the surface of a pot of soup. The star also begins to lose mass. The bloated outer layers are only loosely held by gravity now, so a stellar wind blows them into space, carrying gas and dust away. That dust, formed from cooled atoms like carbon, oxygen, silicon, and iron, will one day be the soil from which new planets grow. The red giant is messy but generous. Inside, the core temperature climbs toward the critical threshold for helium fusion. In a sun-like star, the core is so tightly packed that a strange quantum effect called electron degeneracy appears. The electrons are squeezed until they behave like a stiff spring that resists further compression. This is not dangerous. It's just different physics than we are used to. It means that when the core heats up, it doesn't expand and cool as easily as it did during the main sequence. So the temperature can race upward without the normal thermostat effect turning on right away. The star's brightness fluctuates a little as internal waves and the growth of the shell stir the envelope. Some red giants gently pulse over months or years, like a sleeping giant snoring. Around them, any surviving planets and moons feel strong tides and see their skies filled by the swollen star. Their climates, if they exist, are transformed. In the outer system, frozen objects might warm enough to release gases, forming temporary atmospheres and tails. The red giant stage can last hundreds of millions of years for a sun-like star, a blink compared to the long calm, but still an age by human measures. It ends with one of the strangest moments in a small star's life, the helium flash, the sudden lighting of a new kind of nuclear fire deep in the core. When the contracting helium core finally gets hot enough, around 100 million degrees, helium nuclei, 2 protons and 2 neutrons, can fuse. In sun-like stars, this core is still supported not by normal gas pressure, but by degenerate electrons, which makes the thermostat misbehave. As the first helium reactions turn on, the added heat does not make the core expand and cool right away. Instead, the temperature shoots up and the fusion rate skyrockets. This is the helium flash. Despite the dramatic name, nothing explodes outward. The whole rumble happens deep inside and the outer layers barely notice. The enormous burst of energy goes into lifting the degeneracy inside the core, loosening that stiff spring of electrons so that the core can expand a bit and start acting like a normal gas again. Once that happens, the thermostat returns. More heat makes expansion, and expansion cools the core to a steady temperature. The star quickly settles into a second stable phase, with helium fusing in the core and hydrogen fusing in a shell around it. On astronomers' charts, this is sometimes called the horizontal branch, or the red clump for sun-like masses, but you can think of it as a shorter, calmer middle-aged 2.0. The star shrinks compared to its largest red giant size, gets a bit hotter at the surface, and its colour shifts slightly back toward yellow-orange. In the core, helium fuses into carbon and oxygen, the next steps up the element ladder. The reactions are different. 3 helium nuclei can combine into carbon, the triple alpha process, and carbon can grab another helium to make oxygen, but the effect is familiar. Mass turns into energy, and that energy holds the star up. This phase is shorter than the main sequence because helium is less abundant and burns faster at higher temperatures. For a sun-like star, it lasts a few 100 million years. During this time, the star's wind continues to carry material into space, and the vibrations running through the star, like pressure waves in a bell, can make small regular changes in brightness, useful to astronomers who use those starquakes to probe the interior. As helium runs low in the core, the story repeats in miniature. The carbon-oxygen core contracts and heats. Helium fusion moves to a shell around it, and the outer layers respond by swelling again. The star climbs back up the giant ladder into a phase with even stronger winds and deeper pulsations. That is the gateway to one of the most beautiful endings a small star can have, shedding its glowing skin and revealing the white-hot ember at its heart. Astronomers call this swollen late-life stage the asymptotic giant branch, AGB. The name is less important than the picture, a star with a carbon-oxygen core that no longer fuses, surrounded by a helium-burning shell, surrounded in turn by a hydrogen-burning shell, all wrapped in a huge, cool envelope that pulses like a living lung. The pulses happen because the layers where helium ignites are unstable. They build up fuel, flash, expand and cool, then quiet down until fuel builds again. Each thermal pulse can make the star brighten and fade over years to decades. With every breath, the star's outer layers loosen. A slow, dense wind flows away, thick with newly made carbon, oxygen, silicon, and heavier elements that hitch rides on tiny dust grains. Those grains are not decoration, they are seeds. In the cold of space, they will help gas clump, cool, and eventually form the solid parts of asteroids and planets around some future newborn star. Sometimes convection dredges material from the burning shells up to the surface, changing the star's chemistry in ways we can read from its light, even across thousands of light years. The star can become a carbon star, with more carbon than oxygen in its atmosphere. Carbon molecules then tint the star's light and help form rich, sooty dust. From a planet's eye view, this phase is a sandblaster. The star's wind grows so strong that it can erode anything nearby. The radiation pressure, light itself pushing on dust, helps drive the wind faster. Rings, arcs, and spiral patterns sometimes appear in the ejected material, especially if the star has a companion whose gravity stirs the outflow. In a few 100,000 years, the star can shed a significant fraction of its mass. Because gravity depends on mass, the grip on the outer layers weakens even more, and the wind thickens into an expanding shell that hides the star in visible light. But the core continues to heat as it shrinks. Eventually, after enough mass leaves and the envelope thins, the hot central star begins to ionize the gas around it, lighting it up like a neon sign. That marks the start of the planetary nebula phase. A misleading old name, it has nothing to do with planets for one of the sky's most delicate sights. A glowing bubble or ring sprayed into space by an aging star, shining in soft greens, reds and blues as different atoms light up. The AGB star, having fed the future with dust and elements, is about to reveal what will remain, the dense, white-hot core itself. When the retreating envelope becomes thin enough, the exposed hot core floods the surrounding gas with ultraviolet light. That light strips electrons from atoms in the expanding shell. When electrons fall back, the gas glows. From far away we see a planetary nebula, a round or ring-shaped cloud with intricate filaments, sometimes with jets or symmetric lobes, if magnetic fields or a companion star shape the outflow. The colours are physics made visible. Oxygen often glows green-blue, hydrogen red, nitrogen crimson. Inside this lantern sits the remnant core, now called a white dwarf. A white dwarf is not hot in the way a star is hot from fusion. It is hot because it used to be the star's centre and has been compressed to fantastic density. Imagine the mass of the sun squeezed into a sphere the size of Earth. What holds it up is the same quantum stiffness we met earlier, electron degeneracy pressure. Packed electrons refuse to be squeezed into the same states, and that refusal supports the star against gravity without any new fusion. White dwarfs start very hot, over 100,000 degrees at the surface, but they cool slowly because they are small and have no internal energy source. Over billions of years they fade from white to orange to red to black, like a cosmic ember. The planetary nebula itself is short-lived by cosmic standards. After 10 or 20,000 years, its gas spreads out and blends back into the interstellar medium, the grand reservoir of raw material. The white dwarf remains, a quiet monument to the star's long life. If the white dwarf has a companion star, new dramas can play out. Gas can trickle from the companion onto the white dwarf's surface. When enough hydrogen piles up, it can flash into fusion in a runaway thin layer, causing a sudden brightening called a nova, a surface event that does not destroy the white dwarf. If too much mass is added, and the white dwarf nears about 1.4 times the Sun's mass, the Chandrasekhar limit, the physics that supports it fails, and the entire star can collapse and blow apart as a Type Ia supernova, leaving no remnant at all. Those spectacular explosions are important cosmic yardsticks. But for a single sun-like star with no close companion, the end is gentler. A glowing planetary nebula that drifts into space and a white dwarf that cools forever, while its scattered atoms begin the long journey into new clouds, new disks, and maybe someday, new worlds. Let's stand by the white dwarf and watch time pass. At first, it is a blinding pin in the middle of a fading nebula. Over millions of years, the nebula dims to invisibility, and only the dwarf remains, cooling as it radiates away stored heat. Because it is so dense, its heat doesn't escape quickly. Crystals can form in its interior as the ions settle into an orderly lattice. Yes, a white dwarf can crystallize, turning into something like a planet-sized diamond at heart. Over billions of years, it slides down the temperature scale. There is no more fusion, no more winds, no more bright pulses, just a long, slow fade toward darkness. In an unimaginably distant future, After tens or hundreds of billions of years, it would become a black dwarf, a cold remnant that the current universe is still far too young to have produced. That is one ending for stars. Small and sun-like, they die gently. But mass rewrites endings. Stars are little more massive than the sun can briefly ignite carbon in their cores. Most still end as white dwarfs, but with different mixes. Some are oxygen neon dwarfs. Stars much more massive live fast and die violently. Their cores burn through helium, carbon, neon, oxygen, and silicon in quick succession, building an onion of fusion shells. They reach iron, which cannot give energy by fusion, and then the core collapses, triggering a supernova. The remnant is either a neutron star, a city-sized ball of neutrons, or a black hole, a place where gravity is so strong that not even light can escape. We will take that road in the next acts. Why tell both stories? Because the life cycle of stars is also the life cycle of elements. Small stars like the sun make and spread carbon and nitrogen, the stuff of life's molecules. Massive stars forge the heavier elements and scatter them in supernovae. White dwarfs in certain binaries explode as type Ia supernovae and make much of the iron in your blood and in city steel. Every breath you take contains atoms cooked in stars that died long before the sun was born. The quiet white dwarf cooling in the night is not a failure. It is a gift left on the table for the next generation of stars and planets. In a galaxy's grand economy, nothing truly goes to waste. Gas turns into stars. Stars turn into heavier atoms. Winds and explosions return those atoms to space. Gravity gathers them again into new clouds. The light you see when you look up is not just scenery, it is recycling in action, patient and beautiful. With the gentle path complete, we now turn to the fast lane. What happens when a star is born big, burns hot, and ends with a bang? Some stars are born with far more mass than the sun, 10, 20, even 100 times as much. From the first breath they live in the fast lane. Gravity squeezes their cores so hard that the temperature shoots far higher than in a sun-like star, and hydrogen fuses by a different main route called the CNO cycle, which uses carbon, nitrogen, and oxygen as helpers to push protons together. You do not need the reaction details. The takeaway is simple. Higher temperature means much faster fusion. A massive star burns through its fuel like a race car burning gasoline on a track. Loud, bright, spectacular, and short-lived. Instead of billions of years, many of these stars live only a few million years on the main sequence, and the truly gigantic ones live only a few 100,000 years. Their surfaces are so hot that they shine blue-white and pour out floods of ultraviolet light. That light hits the nearby gas in the cloud that birthed them and turns it into glowing bubbles called H2 regions, pinkish nebulae you may have seen in photos. Their stellar winds are also fierce, streams of particles blowing off the surface at thousands of kilometers per second, strong enough to carve cavities and push on the same clouds where new stars are trying to form. In other words, big stars are loud neighbors. They shape their environment, compressing some pockets, which can trigger more stars, and clearing out others, which can shut star formation down. They also tend to form in clusters, not alone, so a young cluster may contain hundreds or thousands of stars of many masses born together. In such a cluster, the massive ones are the celebrities, few in number, but dominating the light and the weather. A planet near a massive star would see a dazzling blue sun, short seasons before the star changes, and constant particle storms. But because the lifetimes are so short, there is barely time for complex life to get started on any nearby world. Massive stars write their stories quickly. A fast, brilliant childhood, a brief middle age, and then a rapid change as core hydrogen runs out. When that happens, the transition is the same as for the Sun in outline. Core contracts, outer layers swell, but every step is faster and more violent. The star may become a blue supergiant first, then a red supergiant, or it may bounce between these states depending on mass and spin. Either way, the clock is ticking loudly. The core is racing toward temperatures where not just helium, but heavier fuels will light, one after another, like stages in a firework. The supergiant chapter begins. Once a massive star leaves its main sequence, it grows into a supergiant, a star so large that, if placed where the Sun is, its surface could reach the orbit of Mars or beyond. On the outside, it can look cool and reddish, a red supergiant like Betelgeuse, or hot and blue, a blue supergiant like Rigel. On the inside, the core continues to contract and heat while new shells of fusion turn on. The outer layers of a red supergiant are so extended and thin that convection, giant rolling cells, dominates, and the surface can rumble and flicker as blobs the size of our whole solar system rise and sink. These stars also lose mass at astonishing rates. The combination of radiation pressure, light pushing on matter, surface turbulence, and dust formation in the cool outer atmosphere drives winds that carry away a solar mass in as little as 100,000 years. The lost gas does not vanish. It forms a circumstellar envelope, a slow-moving cloud enriched with elements made inside the star. That cloud becomes the stage on which the final act will later play out, when a blast wave tears through it and makes it glow. Some massive stars take a different path and flip between hot and cool states, or become luminous blue variables that erupt unpredictably, shedding shells of gas in titanic outbursts. The star Eta Carinae, for example, ejected several suns' worth of material in the 1800s and built twin lobes of glowing gas we can still see. Why the drama? Because the engine room is changing fuels. After helium lights in the core and makes carbon and oxygen, the core contracts again when helium runs out. The temperature rises high enough for carbon to ignite, then later neon, oxygen, and silicon, each at successively higher temperatures and shorter timescales. The outside world may only notice gentle changes in color and brightness, but inside the star becomes layered like an onion, each shell burning a different fuel. As the layers multiply, the star's stability decreases. Pulsations grow, hotspots appear, and the wind thickens. Gravity and pressure are still in a temporary truce, but it is not the smooth thermostat of the Sun's youth. The star is now a swollen, bright, unsteady lantern, spraying the future elements of planets into space, while rushing toward a limit nature has set. Once the core builds up iron, fusion can no longer pay the bills. When iron dominates, adding heat does not make more energy, it takes energy. That is the cliff's edge. The next act describes the short, frantic sprint through these last fuels and the building of the iron core that will decide everything. If you could slice a dying massive star in half, please don't, you would see nested shells, each fusing a different fuel. First, the core fuses carbon into heavier elements like neon, sodium, and magnesium over thousands of years. When carbon runs low, the core contracts and heats until neon can burn. That lasts only about a year. Then comes oxygen burning, producing silicon, sulfur, and others. This might last months. Finally, silicon burning makes iron peak elements, iron, nickel, cobalt, and it can run for only days. Why does each stage get shorter? Because the core temperature must be higher for each new fuel, and higher temperatures make reactions run much faster. Also, each new fuel holds less total energy to extract per kilogram. Meanwhile, the star continues to shed mass in winds and eruptions, building a complex atmosphere of shells and arcs. The outer layers still shine steadily enough to look like a normal star in a telescope, but the engine room is racing. The energy flow is enormous. Neutrinos, tiny, almost ghostly particles, carry away a huge fraction of the power, streaming out through the star almost without interacting. The core's density becomes staggering, up to billions of kilograms per cubic meter. Electrons are squeezed so hard that their degeneracy pressure, the quantum stiffness that once saved the Sun's helium core from collapse, is now the main thing holding gravity back. But iron group nuclei at the center are a trap. Fusing them consumes energy rather than releasing it, and breaking them apart by gamma-ray smashing, called photodisintegration, also consumes energy. There is no profitable fusion path left, so as silicon burning winds down, the core becomes an iron ball supported only by electron degeneracy. Add a little more mass to that iron ball by ash from silicon burning falling in, and it crosses a threshold. Electrons get pushed into protons to make neutrons and neutrinos, a process called electron capture, which removes the very pressure that was holding the core up. The core's support is yanked away. Collapse begins. In a fraction of a second, the iron heart of the star falls in on itself at a quarter of the speed of light. The next act is the blink and you miss it physics of that collapse, the bounce, the flood of neutrinos, and the birth cry of a supernova. Once the iron core crosses its support limit, gravity wins completely. The core collapses catastrophically, and in about 1/10 of a second, it shrinks from something Earth-sized to something city-sized. As the core compresses, protons and electrons combine into neutrons and neutrinos. The neutrinos race outward in a blinding torrent. For a brief moment, the star emits more energy in neutrinos than all the visible stars in the universe combined, though almost none of that energy interacts with matter. When the inner core reaches nuclear density, the density of an atomic nucleus, neutrons resist being squeezed further, neutron degeneracy, and the strong nuclear force push back. The collapsing material slams into this suddenly stiffening core and bounces, sending a shock wave outward. But the shock stalls as it plows through the infalling layers and loses energy, breaking up iron nuclei. How does the explosion succeed? The leading idea is that a fraction of the sea of neutrinos streaming from the core is absorbed behind the stalled shock, reheating it and pushing it outward again, helped by turbulence and acoustic waves in the boiling matter around the core. In some stars, rotation and magnetic fields add extra push, channeling energy into jets. Once revived, the shock rips outward through the star, turning the overlying elements into a hot, expanding fireball. The star's surface does not know any of this until the shock reaches it. When it does, hours after the collapse, the star suddenly brightens by many orders of magnitude as the shock breaks out, blasting the outer layers into space at thousands of kilometers per second. To anyone watching from a safe distance in a galaxy nearby, a new bright point appears, a supernova, outshining its entire host galaxy for days to weeks. Inside, the remnant left behind is either a neutron star, if the core mass is modest, or a black hole if the core was too heavy to stop collapsing. The timing is wild. Millions of years to live, months to burn oxygen, days to burn silicon, and milliseconds to die. The neutrino flash precedes the light. In 1987, neutrino detectors on Earth caught a handful of neutrinos from a supernova in the Large Magellanic Cloud, a few hours before telescopes saw the star brighten. That was the universe tapping us on the shoulder, saying, "Listen with new ears." Stars shout in many languages. The outward blast now begins its own story. It slams into the material the star blew off in life. It forges new elements in the heat of the explosion, and it seeds the galaxy with everything from calcium in your bones to much of the oxygen you breathe. The aftermath is as important as the blast. The supernova's shockwave roars outward through the star's old winds and into the surrounding cloud. Temperatures and pressures in the shock are so high that new nuclear reactions ignite in the ejector and at the shock front, forging elements heavier than iron by grabbing neutrons in bursts, the R process, and by other hot processes. Dust grains condense in the cooling debris months to years later, fresh solids made from the star's insides. The expanding wreckage becomes a supernova remnant, a growing bubble of hot gas threaded with magnetic fields and tangled filaments, bright in X-rays, radio waves, and visible light where denser knots cool and glow. Famous examples like the Crab Nebula, 1,000 years old, and Cassiopeia, A, about 350 years old, show intricate rings and wisps, scars of the explosion running into the lumpy material the star shed before it died. The shock does more than paint pretty pictures. It compresses nearby gas, sometimes kicking sleepy clouds into forming new stars, and it accelerates particles, electrons and protons, to near-light speeds, making cosmic rays that rain through the galaxy and into our solar system. Those cosmic rays are part of the quiet background that can flip bits in electronics and help spark chemistry in atmospheres. The blast wave also clears cavities, bubbles tens of light years wide, where future supernovae can explode more freely. In star-forming regions, overlapping bubbles carve a frothy landscape that you can see in deep photos of galaxies, shells, arcs, and chimneys where hot gas vents. For any nearby planets, the event is mixed news. At a safe distance of many light years, a supernova is just a light show. Closer in, intense ultraviolet and X-rays can strip atmospheres. The shock's high-energy photons and particles can alter chemistry and damage life. Fortunately, space is big. Harmful supernovae are rare in our neighborhood, and life on Earth has persisted through many in the broader galaxy. Meanwhile, the central remnant, a neutron star or black hole, begins its quieter, longer story, which can turn loud again if it feeds on a companion or if it spins and beams radio waves like a lighthouse. In a few tens of thousands of years, the remnant's gas thins and merges with the interstellar medium. Its atoms, oxygen, silicon, calcium, iron, are now part of the raw material for the next generation of stars and planets. Supernovae are not merely endings, they are restarts. They return enriched matter and stirring energy to the galaxy's pot, ensuring that future suns will rise with planets made of more than hydrogen and helium, and that those planets can be rocky, watery, and alive. If the collapsing core was not too heavy, the death leaves behind a neutron star, an object so dense that a teaspoon of its matter would weigh a mountain. Picture something about 20 kilometers across with more mass than the Sun. Gravity is so intense that atoms are crushed. Electrons and protons have merged into neutrons, and the neutron's quantum pressure, plus the strong nuclear force, now holds the star up. The surface gravity is 100 billion times Earth's. The escape speed is half the speed of light. Neutron stars often spin rapidly because angular momentum was conserved during collapse, like a skater who spins faster when pulling in their arms. Some rotate dozens of times a second, some hundreds. If their strong magnetic fields are misaligned with the spin, beams of radio waves, and sometimes X-rays and gamma rays, sweep through space like lighthouse beams. Each time a beam crosses Earth, we detect a pulse, so we call these stars pulsars. Their ticking is so regular that astronomers use pulsars as cosmic clocks, and in groups as detectors for gravitational waves rippling the fabric of space-time across the galaxy. Some neutron stars are born with magnetic fields so extreme, magnetars, that their fields can twist the star's crust and trigger giant flares that briefly outshine everything nearby in high-energy light. Over long times, pulsars slow down as they radiate energy, and sometimes they glitch, suddenly spinning a tiny bit faster when their superfluid interiors repin and let angular momentum slip outward. Many neutron stars live in binaries. If a companion star orbits close enough, gas can flow toward the neutron star, forming a hot accretion disk that shines in X-rays. These X-ray binaries can flicker and flare as the flow changes. In rare, spectacular cases, two neutron stars in a pair spiral together and merge, radiating a burst of gravitational waves and a flash of gamma rays. The merger tosses neutron-rich debris into space, where nuclei rapidly capture neutrons to forge the heaviest elements, gold, platinum, uranium, in a glowing event called a kilonova. Telescopes saw such a kilonova in 2017, along with the gravitational wave signal from the inspiral. It was a landmark moment that confirmed how the universe makes much of its heavy treasure. Neutron stars are laboratories beyond anything we can build. Matter at nuclear density, magnetic fields that could erase a credit card from halfway to the moon, clocks that rival atomic timekeeping. And yet they are also humble in the grand cycle. The ash of massive stars, cooling and spinning down over millions to billions of years, remind us that even the fiercest stellar lives end in a quiet, steady fade, unless, of course, gravity pushes them one step further into the dark and a black hole is born. Sometimes the collapsing core of a massive star is too heavy even for neutrons to hold up. The pressure that saved a smaller star as a neutron star now runs out of tricks. Gravity keeps squeezing, and the matter falls inward past the point where any known force can stop it. In Einstein's picture of gravity, mass bends space and time. A black hole is what happens when that bending becomes so extreme that space around the core folds in on itself. The surface that separates outside from in forever is called the event horizon. It is not a physical wall, nothing special to touch. It is a one-way boundary. Cross it going inward, and every path the future allows leads deeper in. Light can't climb back out, which is why the thing looks black. Popular culture makes black holes sound like cosmic vacuum cleaners that suck everything from huge distances. That's not right. Far away, a black hole's pull is just gravity, like any object of the same mass. If our sun were magically replaced by a black hole of exactly the sun's mass, don't worry, nature doesn't do that. Earth's orbit would stay the same. Dark and cold, but the same. The drama happens only when you come very close, where gravity changes fast over small distances. There, tidal forces, the difference in pull between your near side and far side, can become intense. Around small stellar mass black holes, those tides could stretch and tear anything that wanders too near. Spaghettification, the memorable nickname. Around supermassive black holes in galaxy centers, the horizon is so large that the tides at the edge can actually be gentle. You could cross the horizon without noticing in that moment, though you could never return. What would you see as you fell? Time near a black hole is strange. To a distant observer, your clock appears to slow as you approach the horizon. Your image redshifts and fades, never quite crossing from their point of view. From your point of view, your watch ticks normally, the outside universe looks sped up, and the horizon is just a place you pass. The black hole's surface is described by a size called the Schwarzschild radius, bigger for more mass. If the hole spins, as real ones do, the horizon and the space around it are twisted. Frame-dragging pulls nearby space into a slow whirl. Most black holes form quietly from stellar collapse, hidden inside exploding stars, or by later mergers of compact objects. We see them by what they do to their surroundings, how they tug on nearby stars, how they light up matter in a disk if they are being fed, how they launch jets, and how they shake space-time when they merge. A black hole is not an evil maw. It is a simple, extreme outcome of gravity writing in boldface. It is also not the end of the star's story for the galaxy. The explosion that happened as the hole was born has already sprayed the star's elements outward. The hole remains as a dark punctuation mark, quiet for ages unless something wanders close, dramatic if it ever gets a meal. A black hole on its own is invisible, but a hungry black hole is loud. Gas that drifts too near doesn't fall straight in like a rock in a well. It has sideways motion and forms a flat accretion disk. Friction and magnetic turbulence inside the disk turn orbital energy into heat. The closer in you get, the faster the gas whirls and the hotter it becomes. So hot that the disk shines in X-rays near the center and in visible and ultraviolet light farther out. That glow, not the hole itself, is what telescopes catch. In small systems where a black hole or neutron star shares an orbit with a normal star, gas can stream from the companion and feed the disk. These X-ray binaries flicker, flare, and sometimes erupt when fresh gas dumps in. Some become microquasars, tiny versions of the powerful quasars seen in galaxy centers. In both small and giant cases, magnetic fields wound up by the spinning disk can focus some of the inflowing energy into narrow relativistic jets, beams of particles moving at speeds close to light. Those jets can punch far beyond the host system, lighting up interstellar or even intergalactic space, and in galaxy centers, helping shape how gas cools and forms stars on scales of tens of thousands of light years. The physics up close is messy, but the big ideas are clear. Gravity makes the gas move. Friction and tangled fields heat it. Heated gas glows. Fields can launch part of it back out in organized streams. If you worry about safety, remember scale. A stellar mass black hole halfway across the galaxy is not a hazard. Space is enormous, and these engines affect only their near neighborhoods. Even the giant black hole at the Milky Way's heart is quiet and far away. It gently nudges star orbits, but does not menace Earth. Feeding cycles can be episodic. Disks fill, heat, brighten, empty, then dim, like a campfire that flares when you toss on brush. In galaxy centers, the rhythm is slower. Clouds drift in. The central black hole has an active phase, quasar or radio galaxy. Then it rests. In that on-off beat, black holes act as thermostats for galaxies. Too much gas tries to cool and collapse into new stars. The jets reheat some of it and puff it out, slowing the burst. This feedback keeps some galaxies from forming all their stars too fast, too early, stretching star formation over billions of years. None of this turns a black hole into a puppet master. It's simply another example of balance in the cosmos. Gravity pulling, pressure pushing, and magnetic fields threading the dance, with light as the ledger of all the energy traded on the way down. Einstein predicted that moving masses would stir gravitational waves, tiny ripples in the geometry of space and time that travel at light speed. For a century, those waves were a beautiful idea on paper. In 2015, detectors with laser arms kilometers long finally heard them, the faint stretching and squeezing of space as two black holes far away spiraled together and merged. Since then, we've heard many such mergers, black hole with black hole, and in 2017 a spectacular neutron star plus neutron star event. Each signal is a three-part song, the inspiral, higher pitch as the pair circles faster, the merger, a sharp peak, and the ring down, the new object, settling and ringing like a bell. From the shape of that song, we can measure the masses and spins and even the distance, turning some events into standard sirens, tools to help check the expansion rate of the universe. When neutron stars merge, the show expands to light. Their tidal wrestling throws off neutron-rich debris that rapidly builds heavy elements. That hot radioactive debris glows for days in a kilonova, bluer early, redder later, as the ejector expands and cools. Telescopes around the world watched one such glow fade after the 2017 gravitational wave alert, and spectroscopy showed fingerprints of freshly minted heavy elements. In other words, gold and platinum can literally be born in such crashes. Black hole plus neutron star mergers are trickier. If the hole is too massive or the spin unhelpful, it can swallow the star whole with little light, leaving only waves to tell the tale. If the neutron star gets ripped apart first, a faint kilonova may still bloom. For black hole plus black hole, waves are our only messenger, but they carry rich information. The total mass, the spin, and clues to how the pair formed. Were they born as a binary, or did they meet later in a crowded star cluster? Listening to the sky this way has changed the game. We are no longer limited to light that interacts with matter. We can feel the pure geometry of motion. The network of detectors on several continents, watching different polarizations and arrival times, acts like a giant ear. And the story circles back to star life. Most of these compact pairs were once ordinary massive stars that lived fast, died as supernovae, and if the explosions didn't fling them apart, continued as a tighter duo. Their final dance and merger are the last chapters of stellar evolution written in waves instead of light, tying together birth, life, death, and a second life as a compact binary that, over millions to billions of years, spirals in and ends with a whisper we can now hear. Stars tend to be born in groups. A giant cloud rarely collapses into a single object. It fragments into many, making a family, from a few dozen newborn suns in a loose association to thousands in a dense open cluster. These families drift apart over hundreds of millions of years as gravity from the galaxy stretches them and close encounters fling members outward. While they are young and together, their shared age and chemistry make them wonderful laboratories. By plotting their brightness and colour on a graph, the Hertzsprung Russell diagram, you can see a single curve peel away from the main sequence at a point that tells you the cluster's age. Far older and denser are globular clusters, spherical swarms of hundreds of thousands of stars, most more than 10 billion years old, orbiting the galaxy like bees around a hive. Their stars are metal poor. Astronomers call any element heavier than helium a metal, meaning they formed early, before many rounds of stellar life enriched the gas. In any cluster, the initial mass function, how many stars of each mass were born, tilts heavily toward low mass. The sky makes many small, few big. That crowding and balance shapes fate. Close passes can swap partners in binary systems, or even smash stars together to make blue stragglers, mysteriously young-looking stars in old clusters that likely gained mass by merger or transfer. Dense cores can be nurseries for X-ray binaries and compact object pairs that will one day merge and ring the detectors on Earth. Cluster environments also test how metallicity changes star behavior. Metal-rich stars cool and form molecules more easily. Metal-poor stars shine differently and lose less mass in winds, changing how they die. Zooming out, whole galaxies have personalities. Spirals with gas keep forming stars in their arms. Ellipticals, often gas-poor, form most stars early and then coast. Galaxy collisions can trigger starbursts, short, furious episodes of star birth, followed by quiet spells when feedback from supernovae and central black holes blows gas out or keeps it too warm to collapse. At the very beginning of cosmic time, the first stars, nicknamed Population 3, were probably very massive and short-lived because the gas then had no metals to help it cool into small fragments. Their supernovae seeded the young universe with the first heavy elements. Every star, then, is both an individual and a citizen. Its mass and spin write its personal script, while its neighborhood, companions, cluster density, galaxy type, and cosmic epoch adds plot twists. To read a star's life, astronomers always ask two questions. How big were you at birth? And where did you grow up? Bringing the story home makes it real. Our Sun is about 4.6 billion years old, a middle-aged, steady star with another few billion years of calm hydrogen burning ahead. During that time it will brighten slowly, roughly 10% every billion years, because helium ash building in the core raises temperature and fusion rate. Long before the dramatic phases, that slow brightening will reshape Earth's climate. In hundreds of millions of years, increased sunlight will likely push our planet into a moist greenhouse, warming the oceans and accelerating water loss to space. That is a long, long runway for life and for any civilization that might plan for distant descendants. After roughly 10 to 11 billion years of total age, the Sun will exhaust hydrogen in its core and begin the path we traced for Sun-like stars. Subgiant expansion, then the true red giant stage. It will inflate to dozens, then perhaps 100 times its current diameter. Mercury and Venus will be gone. Earth's exact fate is a tug-of-war between orbital expansion. As the Sun loses mass, orbits drift outward and drag in the Sun's swollen atmosphere. Most studies suggest Earth will be engulfed or stripped, though it is a close call. The outer planets migrate a little but survive. The icy worlds of the Kuiper Belt bask in newfound warmth. After the helium flash, the Sun will briefly settle into core helium burning, then swell again into the AGB phase, pulsing and casting off shells of gas and dust. Finally, the hot core will light the ejected gas into a soft planetary nebula, a beautiful, short-lived bubble. At the center will remain a white dwarf roughly the size of Earth and about half the Sun's mass, white hot at first, then cooling for billions upon billions of years. That ember is the Sun's final self. The timeline is huge. Red giant drama in about 5 to 6 billion years, planetary nebula not long after, and white dwarf cooling that outlasts continents, languages, even the shapes of galaxies as we know them. Nothing here is a near-term threat. It is a distant, predictable arc. If there are far future beings around Saturn or on wandering habitats near the outer planets, their night skies will hold a huge orange sun for a time, then a delicate glowing shell, then a pinpoint ember. They will be able to point and say, "That's our star's heart, cooling." It is strangely comforting. The Sun is ordinary. Ordinary here means reliable, understood, and kind to planets for a very long time before it changes. Its end, when it comes, will also be ordinary for stars like it, not a bang, but a gift of gas and dust to the galaxy, and a quiet white dwarf that for ages will shine enough to be a small sun for any objects that remain. Planets do not simply wink out when their star changes, they react. Close-in worlds around a red giant can be swallowed, baked, or stripped to their rocky cores. Farther out, some planets migrate outward as the star loses mass and gravity's grip weakens. Moons can be tugged loose. Small bodies are perturbed into new paths. In the chaos near the end, asteroids and comets can be nudged onto paths that skim the bloated star's atmosphere and evaporate, or they can be flung outward to become rogue planets and interstellar debris. After the envelope is gone and a white dwarf remains, the system settles, but not into silence. Many white dwarfs show heavy elements, metals, in their thin outer layers. That is a clue, because heavy atoms should sink quickly in such dense, hot atmospheres. Their presence means the white dwarf is actively eating small amounts of rocky material, dust and crumbs from disrupted asteroids, or fragments of dead planets that wandered too close and were torn apart by tides into rings that slowly rain down. In a few systems, we can even see the debris disks glowing in infrared light, or catch the silhouette of a disintegrating minor planet crossing the white dwarf. This is archaeology in real time, the ashes of planetary systems being sorted by gravity and fed back to the star in spoonfuls. There are stranger tales. A handful of pulsars, rapidly spinning neutron stars, host planets, likely built from fallback debris or captured material after the supernova. The first exoplanets ever discovered were around such a pulsar, a shocking result that taught us planet formation is robust and opportunistic. Around red giants, habitable zones move outward. Icy moons and dwarf planets can briefly thaw, making seas where none were before, though tides and radiation will be harsh. Around white dwarfs, a slim habitable ring exists where a small, rocky world could, if it somehow arrived there later, stay warm from the white dwarf's gentle light for billions of years as it cools from blue-white to orange to red. Moving a planet there naturally is hard, but not impossible. Gravitational pinball with other worlds can do wild things over long times. The big picture is that planetary systems, like stars, evolve. They are built from disks, sculpted by gravity, weathered by radiation, shaken by close encounters, and rewritten when the star sheds mass. The evidence hides in crater ages, in odd orbits, in dusty rings, and in the chemistry of white dwarf atmospheres. To anyone who loves worlds, this is bittersweet. Some places are lost. New niches appear, and the ingredients, water, carbon, silicates, metals, do not vanish. They are recycled into fresh clouds that will someday make new disks and new planets around newborn suns. In that sense, even a star's death clears the stage for the next act of world making. Astronomy's superpower is that we can learn almost everything about a star from the light that reaches our eyes and instruments, even though we will never go there. Start with the simplest measurement: brightness. With careful photometry, light counting, we track how bright a star appears from Earth. If we also know its distance, we can compute its true luminosity, how much energy it really emits each second. Next comes colour, which is not just aesthetics, but a thermometer. A star that looks bluish-white has a hotter surface. A star that looks orange or red is cooler. By comparing brightness through different filters, for example blue and visual, we get a colour index that maps to temperature. Then we pass a star's light through a prism and record a spectrum, a barcode of dark absorption lines and bright emission features. Each chemical element leaves its own pattern: hydrogen, helium, sodium, calcium, iron, and dozens more write signatures across the rainbow. From those lines we read composition, how much of each element, surface gravity, broad pressure-broadened lines hint at a compact star, sharp lines hint at a puffy giant, temperature, some lines strengthen or weaken with heat, and motion. Motion, yes. If a star is coming toward us, its lines are shifted slightly toward the blue. If it is moving away, they shift toward the red. This Doppler shift lets us measure radial speed to meters per second with modern spectrographs, sensitive enough to see a star wobble under the tiny tug of an orbiting planet. Combining Doppler data with the timing of a planet transit, when the planet crosses the star's face and slightly dims it, gives us a planet's mass and size, and from that, its density, rocky like Earth, or puffy like a gas giant. Stars also carry clocks inside them. Many gently ring with sound-like waves that make their surfaces rise and fall by meters. We cannot see the motion, but we can see the tiny brightness changes it causes. This is asteroseismology. For the Sun, helioseismology, and it works like ultrasound for stars. The pattern of oscillations reveals the star's internal layering, age, and sometimes its spin. To know how far away the star is, we use parallax, the slight apparent shift in position as Earth moves around the Sun. Nearby stars shift by tiny angles measured in milliarc seconds. The European Gaia mission measures these shifts with breathtaking precision for more than 1 billion stars, drawing a 3D map of our galaxy. For a few large stars, we can even measure the angular size of the disk using interferometry, combining light from widely spaced telescopes to create a virtual mirror as large as the separation. And binary stars, two stars orbiting each other, are nature's weighing scales. By tracking their orbits, we get the star's masses directly, the most precious number in a star's life story. Put these tools together, and we can place a star on the Hertzsprung-Russell diagram, the master map of stellar life that plots luminosity against temperature. Where a star sits on that map tells us its phase. Main sequence, giant, supergiant, white dwarf. And how it will move across the map tells us what comes next. All of this from photons that left a distant surface long ago, crossed space undeflected, and surrendered their information to a prism and a patient mind. That is how we touch stars, with light. Distances in space are hard because we cannot lay down a measuring tape between stars. So astronomers built a ladder of methods where each rung supports the next. The first rung is parallax, the same trick your brain uses to sense depth. Close one eye, then the other. Your thumb seems to jump against the far wall. Earth's orbit provides a 6-month baseline. Nearby stars shift against the far background by tiny angles. With parallax, we anchor distances out to thousands of light years directly. The next rungs use standard candles, objects whose true brightness we can infer from some other property. The most famous are Cepheid variable stars. These stars pulse in and out with periods of days to months, and the longer the period, the brighter the star intrinsically. Measure a Cepheid's period from its light curve, measure how bright it looks, and the difference tells you the distance. Cepheids are bright enough to be seen in nearby galaxies, so they carry the ladder across intergalactic space. For very old, dimmer systems, R Lyrae stars do similar work in globular clusters. For greater distances, we use Type Ia supernovae, explosions of white dwarfs in binary systems that reach nearly the same peak luminosity everywhere after a small correction for how quickly they fade. Because they are so bright, they can be seen in galaxies billions of light years away, and they map the surprising discovery that the expansion of the universe is accelerating. Other useful rungs include the Tully-Fisher relation, brighter spiral galaxies rotate faster, the surface brightness fluctuation method, graininess, of unresolved stars correlates with distance, and for very fast scales, redshift, the stretching of light as space expands, calibrated by the Hubble-Lemaitre law. Recently, we gained a new kind of ruler, gravitational wave standard sirens. When two neutron stars or black holes spiral together, the wave signal encodes the distance directly from the physics of the inspiral. If we can also identify the host galaxy and measure its redshift, we get an independent check on the expansion rate. Every rung needs calibration. Parallax calibrates Cepheids in our galaxy. Cepheids calibrate Type Ia supernovae in nearby galaxies. Supernovae map the deep universe. Missions like Gaia sharpen the lower rungs so that the upper rungs sit on firmer ground. The ladder metaphor hides a lot of care. Dust can dim light and trick you about distances, so we correct for colour changes. Some candles are not perfectly standard, so we apply empirical corrections. But the concept is simple. Start with geometry you can trust, reach to candles you can read, then to brighter beacons, and finally to the grand drift of galaxies. With that scaffold, we turn the night sky from a flat dome into a 3D landscape, and we can place each star's story in its proper neighbourhood and era. The early universe made almost only hydrogen and helium with a pinch of lithium. Everything else, the carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, the silicon in rocks, was built later, inside stars and in their deaths. During the long calm of the main sequence, stars fuse hydrogen into helium. When that stage ends, helium fuses into carbon and oxygen in small and sun-like stars. In their swollen late lives, these stars dredge up newly minted elements, fold them into cool winds, and blow them into space as dust, soot-like grains of carbon, and tiny crystals of silicates. Those grains float in the dark between stars, radiating in infrared light, clumping and acting as the first surfaces where molecules assemble. In massive stars, the core goes beyond helium. Carbon burns to neon and magnesium, oxygen burns to silicon and sulfur, and silicon burns to iron peak elements. When fusion stops and the core collapses, the supernova blast rips through the star and its surroundings. In the explosion's furnace, and by capturing neutrons in frantic bursts, the R process, nuclei leap to heavier elements beyond iron. Some of those heavy elements are also forged when neutron stars merge, as we saw in the glow of a kilonova. The universe literally sprays out gold and platinum in such crashes. Even white dwarfs play a role. In Type Ia supernovae, they produce a flood of iron and nickel that later decay and power the supernova's light. Over billions of years, this stellar alchemy enriches galaxies. New stars form from gas that already carries a mix of heavier elements and that changes everything. Gas cools faster, clouds fragment into smaller pieces, more low-mass stars are born, planets build more easily because there are more solids, and the chemistry of life has more raw material. We can read this history in metallicity. Stars near the Milky Way's centre tend to be more metal-rich than those in the halo. Old globular clusters are metal-poor. Young open clusters in the disk are richer. Our Sun is moderately metal-rich, a clue that it formed after many generations of stars had lived and died. Meteorites still carry isotopic fingerprints, tiny excesses and deficits of certain atoms that point back to different kinds of stellar sources. AGB winds, core collapse supernovae, Type 1a explosions. Even water has a story. Icy bodies likely delivered much of Earth's water, with deuterium to hydrogen ratios that trace particular birthplaces in the early solar system. So when we say we are stardust, that is not poetry, it is inventory. The carbon in your DNA likely came from a red giant's wind, the oxygen in your bloodstream from a massive star's core, the iron in your hemoglobin from a white dwarf supernova, the iodine in your thyroid possibly from a neutron star merger. Stars do not simply light the universe, they compose it, passing along richer material each cycle so that galaxies evolve from plain hydrogen fogs into workshops capable of building rocky planets, oceans, and minds that can notice. Given gravity's eagerness to pull gas together, you might expect galaxies to collapse their gas into stars quickly and be done. They don't, and the reason is a balance between star formation and feedback. The energy stars return to their surroundings. Start with a cold molecular cloud. turbulence, magnetic fields, and a little heat support it against collapse. Pockets that get slightly denser start to fall inward, and a small fraction of the cloud's mass, often only a few percent, turns into stars before starlight, winds, and supernovae stir and thin the cloud again. Massive newborn stars flood their cradle with ultraviolet light that ionizes gas, carving glowing bubbles. Their winds sweep shells that bang into other shells, sometimes triggering new pockets to collapse, and sometimes dispersing the gas. After a few million years, the first supernovae detonate, driving shockwaves that can tear the cloud apart. The overall result is self-regulation. You get a burst of star formation, feedback rises, clouds disperse, the burst ends, new clouds gather, and the cycle repeats. On galaxy scales, spiral arms act like traffic jams for gas, compressing it as it orbits and setting the rhythm for starbirth in patterns you can see in photographs. Blue clusters where stars are young, redder regions where older stars dominate. In some galaxies, especially when galaxies collide or interact, gas is pushed into the center and you get a starburst, a short, furious episode where stars form 10 or 100 times faster than normal. Even then, feedback and sometimes the activity of the central black hole, jets, radiation, blow gas back out or heat it so it won't collapse soon, preventing a runaway. At the other extreme, some galaxies grow quiescent. They keep their stars but lose or heat their gas and stop forming new ones for long stretches. Environment matters. Galaxies in clusters can be stripped of gas by the hot intracluster medium as they plow through it. Lonely galaxies out in the cosmic field sip gas more gently from intergalactic filaments. The net effect, averaged over billions of years, is a galaxy that turns only a modest fraction of its gas into stars at any moment, stretching star formation across cosmic time. This is good news for complexity. If everything burned early, there would be fewer long-lived stars, the little red ones that can shine for trillions of years. Fewer chances for planets to form late with rich chemistry and less time for life. Feedback can look like waste, blowing precious gas into space, but it is also gardening, pruning here, stirring there, and leaving enough fuel for the next season. In that garden, stars are both the harvest and the gardeners, setting the pace at which their galaxy stays alive. The future of starlight stretches far beyond human imagination. The most common stars are the smallest red dwarfs, with masses from about 1/10 to half the Sun's. They sip hydrogen slowly and are often fully convective, which means the fuel gets stirred from surface to core and used efficiently. While big stars burn bright and die young, these little stars can shine for trillions of years, hundreds of times the universe's current age. They do not swell into enormous red giants the way the Sun will. Theory suggests they may contract and heat, becoming blue dwarfs late in life before finally fading into white dwarfs. As eons pass, star formation will decline because galaxies will use and lock up their gas in stars and remnants, and because processes like feedback and cosmic expansion make it harder to gather fresh fuel. The Milky Way and Andromeda will merge in a few billion years, forming a larger, more rounded galaxy where gas may be used in a final bright wave of starbirth and then quiet. Long after that, the sky will be ruled by stellar remnants, white dwarfs cooling to black dwarfs. Hypothetical, because the universe is still too young to have any. Neutron stars slowly spinning down, and black holes that simply persist. Occasionally, a white dwarf pair in a tight orbit will merge and set off a Type Ia supernova, briefly relighting a patch of the universe. Even more rarely, a few theorists have imagined that in the far, far future, some black dwarfs might reach conditions for a faint black dwarf supernova, through exotic, slow nuclear reactions, but this is speculative and unimaginably distant. If protons eventually decay, another speculation from some particle theories, matter itself would slowly dissolve over timescales many orders beyond anything we measure. If not, cold remnants might last essentially forever. Black holes might slowly evaporate by Hawking radiation, a whisper of energy leaking from their horizons, but even a stellar mass black hole would take far longer than 166 years to vanish. Supermassive ones would outlast that by absurd factors. All the while, the expansion of the universe continues, and because it seems to be accelerating, distant galaxies will slip beyond any one galaxy's horizon, still there, but no longer in causal contact. None of this is cause for sadness. It is a clear-eyed view of physics at work over deep time. For an almost immeasurable span, red dwarfs will keep gentle fires burning. Planets around them may host seas and skies under dim red suns. Civilizations, if they arise, will have patient calendars. The universe will grow quieter and darker, but not empty of stories, just slower ones, written in embers and in the faint ring of a black hole's last sigh. We can now say the life of a star in one breath and feel it in full. It begins in a cold cloud, where a denser pocket starts to fall inward, spinning up and flattening into a disk that already carries the seeds of worlds. A protostar swells, feeds and sheds jets, then crosses an invisible threshold. Fusion in the core ignites, turning gravity's squeeze into steady light. On the main sequence, the star is a balance of inward pull and outward pressure, a long calm in which hydrogen becomes helium and the star's light powers everything around it. Weather, chemistry, maybe life. Mass writes the rest. Small stars sip for trillions of years. Sun-like stars glow for billions, swell into red giants, flash helium, breathe heavy elements into space, and end as white dwarfs beside delicate planetary nebula. Massive stars rush through fuels like a stack of torches, build an iron heart, collapse, and blast as supernovae, leaving neutron stars or black holes and seeding galaxies with oxygen, silicon, calcium, iron, and more. Along the way, stars live in families, clusters and galaxies, where their births and deaths regulate the next generation. We learn all this not by visiting, but by reading light, brightness, color, spectra, tiny pulses, and minute shifts that reveal temperature, composition, motion, size, mass, and age. By measuring parallax and climbing a distance ladder of standard candles and now standard sirens. By mapping debris glowing in X-rays and radio. By feeling space-time tremble when compact objects merge. The punchline is personal. The atoms in us were put together in stars that lived and died before the sun formed. Our planet's rock, air, and water are second-hand goods in the best sense, well mixed, well travelled, and proven by time. When we study a star, we study our own ingredients and our future, how stable our sun is, how it will change, and how worlds fare under different skies. The story matters because it grounds wonder in understanding. We see that nature is not random noise, it is patterns, thermostats that hold a star steady, feedbacks that keep galaxies from burning out, ladders that let us reach across gulfs with simple geometry and careful calibration. And the story connects scales. The fusion in a tiny core sets the climate of a planet billions of kilometers away. A merger of two city-sized remnants sprinkles a galaxy with precious metals and rings the universe like a bell we can now hear. If you step outside tonight, pick any star. Behind that small glitter is a whole biography like the one you've heard, a beginning in the dark, a long bright middle, a creative end, and a gift to whatever comes next. That is the life of a star, and in a practical sense, the life of everything that can look up and wonder. Thank you for watching, and good night.